Right, so now we have to learn how to run this test. I know it's going to shock you, but it's got 6 steps. And if your p-value is less than alpha, you're going to reject. Now, this is using a different distribution than we've worked with before. It looks a lot like the chi-square distribution. It's going to be right skewed, and it has degrees of freedom. It is not the chi-square distribution, but suffice to say it has its own distribution. It's right skewed and all that good stuff. You still need all these requirements, that it's independent, that it's random samples, and all that good stuff. Normal distributions. Fabulous. And we've already gone over the null and alternative hypotheses. Now, I left in the calculator instructions for no good reason, but if you want to read them, there they are. And then the formula parts. So MyMathLab asks you to find some of these things from other pieces. So I just wanted to put this in there, that the mean squared error, MSE, mean squared error, is the sum of squares due to error, SSE, divided by the degrees of freedom for error, which in case you're interested is n minus k. That's the formula for that. And then this is the formula for SSE, right? If you had to, you could plug in all the numbers, right? And then MST is SST, the sum of squares due to treatment, or factors is sometimes called, divided by the degrees of freedom for those treatments, right? Which is k minus 1 is degrees of freedom. And then again, here's the lovely formula. It's not pretty, but you know, if worst came to worst, you could do it. All right, so let's find the f-test statistic, which is this MST formula, this guy, divided by this MSE formula, this one. Okay. Now, I haven't done with a calculator here, but we're going to do it with StatCrunch because, heck, we have it available to us and it's easy. So I'm going to take these lovely columns of data. I'm going to go to StatCrunch. Oops. All right, I pressed that. And I'm just going to kind of go over here. I don't really need all this stuff before. This was chapter 12 stuff, but that's all right. Just go over here and paste it in. All right, so stat. Hey, look, ANOVA, one way. Cool. I was going to say, okay, where are your columns? What do you want me to compare? I want you to compare ads, music, and classical. All right. We don't want to do this. We won't bother with the 2 key thing. Compare values. We're not doing a single column, so we won't worry about that. So we're just going to click calculate. And there it is. Beautiful, huh? Oops, I didn't mean to print. Huh. Copy. There we go. And let me go to Excel, our chapter 12 and 13 technology thing. Oh, I don't need that. That was just me talking. All right, I'm just going to copy and paste it in. All right, I'm going to label this. This is 13.1 example. Oh, what was it? I know I did it with a calculator, but you should be able to do this. Example 5. Cool. So you can see it's giving us a lot of information. And hey, there are those mean values we found before, and the standard error is right there. Not standard deviation, but the standard error. So that's useful. And then sum of squares and all that good stuff. Okay, so we've now proven that we know how to do this. I'm going to save, Control S, this lovely spreadsheet, and put that down there. All right, now reading calculator output, one of the reasons I left this in here is that it's kind of a pain to read, and you never know if you might be forced to on an exam or something. So can we analyze this? So we have this ANOVA output. The sum of squares due to error, luckily, is written right here, error, which was 139.2. Now in your Minitab output, it's right here, 139.2. See right there? Sum of squares due to error. And degrees of freedom was 12, and the mean squared due to error was 11.6. Now you could find it by hand by taking the 139.2, which is right there, sum of squares due to error, dividing it by that degrees of freedom, 12, and you could get 11.6. So there you go. If you're asked to do it by hand at gunpoint, you now know how. Now the treatment, sometimes called factor, depending on their program. So the sum of squares due to treatment was the 149.2. You divide it by the 2, which was your degrees of freedom, right? And if you did that, 149.2 over 2, that would give you 74.6. That's your mean square due to error. So we found it by hand, taking 149.2, dividing it by 2. But if you didn't, it's still right there, 74.6. Now that f-test statistic, I mean, if you know nothing else, when you look at hypothesis testing, you want to look for your test statistic and your p-value. So your test statistic is 6.431. and this is right skewed, so that doesn't really mean much, but when you look at your p-value, you can see it's 0.0126, which hopefully you're at the point where you know that means you're going to be rejecting the null hypothesis, right? So you draw kind of a right skewed distribution. This is actually very badly right skewed. It has to do with the degrees of freedom, especially that 2, and for one of the degrees of freedom, that's not good. But anyway, so the F is 6.431, so just kind of draw right skewed, put 6.431, label your p-values 0.0126. That is not, that is smaller than alpha, very small, so we are going to reject the null hypothesis. That would be significant, right? That means that we've just shown that there is enough evidence to support the claim that at least one of the wait times for ads, Muzak, or classical music was different than the others. Now, real quick, I just want to show you something. When I went into StatCrunch, oops, you probably won't get used to that. So I can go to options, I can go to edit, and kind of go back to what we were looking at. Just for the fun of it, I'm going to click on this Tukey thing right here, which is not my last name. It was a professor somewhere. You can see that it kind of gives you a little bit more output. It's giving some confidence intervals down here. Right, see that? So you can see, oh, hey, zero's in that confidence interval, -8.3 to 3.14, excuse me. And classical, there we go, we got that one in. So this is the difference between advertisements and Muzak, advertisements and classical. They're not very different because zero's in the interval. But look at Muzak and classical. See how zero's not in that interval? Nice, huh? So if you wanted, you could copy all of that and put it into your Excel. It's the same thing we already did, I know, but you don't have to. The deal is, hold on, although it would help if it would actually work. Copy. There we go. Oh, it's not liking me. Well, it's just not going to do it. And that's fine. I didn't really need it anyway. But I just wanted it to back up what I had said before, which is the classical and the Muzak are where the difference is at. You can see it in this box plot. See, right there? That confidence interval thing we were just talking about is talking about the difference between these two. And the difference doesn't have 0 in it, which means it's significant. So that's another way you can tell if you ever click on the little Tukey thing. We're not going to get much more into it than that. But there you go. Judging from the box plot and from that confidence interval thing we just saw, the classical and the Muzak are the ones that are far apart. And again, it has to do with the fact that 0 is not in their confidence interval. So if you look at Muzak from classical, it's positive to a positive number. 0 isn't in there. Not true for ads. Advertisement wasn't significantly different from the other two. So that's how you can tell. Either that or just look at the box plot and kind of see, hey, which two of the box plots don't overlap. Muzak doesn't overlap with classical. That's where your big difference is. All right, now scrolling down. There we go. All right, so a recent study investigated whether the amount of information a professor posts about themselves, that is called self-disclosure, on Facebook is related to student motivation. A professor constructed 3 different Facebook sites, one each for low, medium, and high self-disclosure. I will let you read this. Pause me for a second and read it. Okay, so hopefully you read it. So we've got our 3 different groups: high disclosure, medium disclosure, low disclosure. I've got a normal probability plot right here. Right, all good. So judging from this, are we okay from doing an ANOVA? So yes, this was 3 random samples. You can tell because it says randomly right here. They were randomly assigned. Are they independent? Well, sure. I mean, if I'm in a study, it doesn't have any bearing on what you believe about this professor or whatever. We don't know each other. We're randomly assigned. So sure. Are they normally distributed? Yep. You can see it right there. The box plots show that they're normally distributed. The normal probability plots show they're normally distributed. The variances we don't know about. There's a whole other test to conduct, but we don't know that. So we're just going to have to kind of say, sure, we're fine, because we don't have enough information for that. So then I give you outputs from Excel. Ooh, there's an Excel output. We haven't seen one of those in a long time. StatCrunch and Minitab. And I highlighted different things. So I just put the high group in blue just so you could see it, but I could have done it for medium and low just as easily. Statistic and the p-value. P-value is always good to look for. And then you got all this mess in here with the degrees of freedom and your sum of squares and your mean squares and all that jazz. That's in the red. So the first thing I asked was just look for the high group. So how many people did they have? What's their mean? What's their standard deviation? So Minitab is real easy. N is 43, so there was 43 in the group. Mean was 81.27, standard deviation is 12.4. Excel, there's 43 in the group, 81.27 is the average. They give you variance here, so you'd have to take the square root of 153.77, which I think I wrote right there, which would get you 12.4. StatCrunch is actually the worst for this. StatCrunch gives you the standard error. You can see the N and the mean is 42. But for StatCrunch, you'd have to do, let's see, S over the square root of N is equal to S over the square root of 43 is equal to 1.89. You have to find the square root of 43 and you'd have to multiply both sides by that. So that's how StatCrunch would do it. It's not pretty, but you could manage it if you had to. Okay. All right, next. Judging from those confidence intervals on that Minitab output right here, see, just sort of a glorified version of what we were seeing from StatCrunch. But this is a different problem, obviously, but it's those kinds of things. So you can see, hey, look at these confidence intervals. Does it appear that somebody's different? Yes, right? We expect to reject the null hypothesis because you can see the low group is not overlapping with these other two. So you bet you're going to show there's a big difference between these groups. All right, find the following. Sum of squares due to error, degrees of freedom for error, and mean squared due to error. The error stuff, they kindly just label it error, 127, 25985, and 205. Same here with error for StatCrunch, easy to read. Excel calls it within groups. So there it is with Excel, 25985, 127, 204.6. So that's what I wrote right there. I rounded, but you know, it's all good. Now treatment, 3355, 2, and 1677. Treatment tends to be real near the error. So Minitab calls it a factor. Factors, treatments, they get kind of interchangeable for these computer programs. Treatments, StatCrunch very kindly calls them treatments. That's lovely. And then Excel, stupid Excel, calls it between groups, right? So, which is actually great. I mean, that's actually more what it is. So Excel's kind of awesome that way because it's letting you know, hey, that's between groups variation, that's the treatment stuff, and then the within groups variation, that's the error stuff. So it's probably better, I know, but I just get frustrated. Yeah. So be able to look at any of those three programs and be able to pick that stuff out. The test statistic is 8.197. The p-value is 0.004. Luckily, those things are never hard to find, no matter what program you're in. P-value F, p-value F, p-value F. All good. And hopefully we all know by this point in the course that if your p-value is that low, you're going to be rejecting, which we'll see down here. In the meantime, you just draw kind of a very badly right-skewed distribution. That's your F distribution. You put 8.197 and label the p-value 0.0004 above it. And you'd say, yep, you know, our p-value is that small, which is less than alpha, so we are definitely going to reject the null hypothesis. That means that there was enough evidence to support the claim that at least one of those population means is different from the others. Judging from the history, judging from the confidence intervals, it would appear that the low disclosure group is significantly different than the others. Which might be interesting to you as either a professor or a teacher or a psychologist. You know, if we expose bits of ourselves, even if it's just at the medium level, does that help our students become better learners in our classroom and stuff like that? But that's all stuff to ponder as you take statistics on to other and bigger things. So we're done with section 13.1. I hope you enjoyed it. Don't forget to save your Excel spreadsheet so you can upload it if you're one of the online students. All right, I'll talk to you guys later. See you in more videos.